This is a continuation on the emission spectra of hydrogen. So I made a mistake in the last video. Rydberg's constant should have a factor of 10 to the 7 and then per meter. So please correct your Rydberg's constant. Okay, so let's try to work out an example. So let's ask, what is the energy needed from a photon so that an electron jumps from n equals 1 to n equals 2. Okay, so an energy is needed for a photon, for an electron to jump from n equals 1 to n equals 2. So we have here 1 over lambda equals Rydberg's constant, which is 1.097 per meter times, so what do we have? Initial 1 over initial square minus 1 over final square. So its initial n is 1 square minus 1 over 2 square. So we would get 1 over 8,822,7,500 per meter. So this is 1 over lambda. So dividing it by 1, we have lambda. So we would get, if we divide this term by 1, we would get 121.54 times 10 to the minus 9 in meters. So we say that it is also about 121.54 nanometers. So this is a wavelength of light that is in the ultraviolet spectrum. So it will have an energy of a UV light. Okay, so we could go on with changing these values, which are the finals from 3, 4, 5, and so on, and we will see that they will all give an energy of light in the UV spectrum. So this behavior is actually observed by Lyman, and he called it the Lyman series. So the Lyman series is the series of UV wavelengths that is required for light so that it can jump an electron from the ground state n equals 1 to all other states here. So similarly, if we start at n equals 2 and jump to the higher states, that series is called the Balmer series. For n equals 3 to the higher states, we call that the Paschen series. And there's so many series, but the important thing to note is that if an electron jumps from one state to another, there is a series of wavelengths of light associated to it.